Hello students, so we are having the new problem of a simple harmonic motion, and the question is a uniform plate has mass capital M. The coefficient of friction is given between the wheels and the plate. If the plate is slightly displaced along the length, you have to calculate the time period of oscillation of this plate. So let us discuss how to tackle with this question, and let's check the equilibrium position. Look at the first story. If you mark symmetrically, so what is happening in the first state? You are having mg of the plate. As it is symmetrically placed, both of the wheel will give the same contact force, the same normal direction. Look at the motion of the wheels, and definitely we have to draw the frictional forces, as you know already. But can you tell me what is so special about this? If you take the frictional forces of both of the wheels, both forces are same. That means this is the situation, which is a situation of equilibrium. And what the question says, the symmetrically placed plate has the distance L by 2 each from the wheel. So let us discuss what will happen if this plate is slightly displaced in one direction. Suppose this plate is displaced slightly by a distance, suppose y. Now your plate is not symmetrically on the two of the wheels. The contact forces will change. Suppose you have displaced the plate along its length by a small distance of y. So what will happen? This is your mg, this is your weight. What will happen? This is L by 2 that was already there. It will increase a little bit from here by a distance y. And what will happen? L by 2 minus y from here. Your plate is not symmetrically distributed on these two rotating wheels now. The contact forces will definitely change. Not only the contact forces, but your frictional forces will also change. Let's find out which of the frictional force will increase and which one decrease. So we have moved the plate towards right by a small distance y. So let's check it out. What will happen when we displace the plate by a small distance from the equilibrium position? So at this position, let us check the forces in equilibrium. Have a look on that. The forces along y-axis, N1 and N2. The forces which are balancing it, this is mg. Second one, if taking another condition of equilibrium where you know that the movements about a given point can also get balanced, let's take the movements. Taking the movements about g, I'm taking movements about g. Let's take the movement for n1. The perpendicular distance from g is L by 2 plus y. If you take the movement of n2, this becomes L by 2 minus y. And you know that from with respect to g, if the one of the movement is clockwise, the another movement is anti-clockwise. So have a look on that. And for the rotational equilibrium, we take the second one as this one. N1 L by 2 plus y become N by 2 L by 2 minus y. Using the first equation, if you find out the value of N2, you can fill it in this equation. L by 2 plus y, N2 is mg minus n is L by 2 minus 1. It's very easy to solve this equation. Let's find out the value of n1. The value of n1 you will get as mg divided by 2l, and I hope you will get it very easily that this one will be the n1. If you fill this n1 into this value, you will also get the value of n2, and the value you will get is this one. Look at the very special thing, n1 and n2 that was previously same, but after displacing your slab by a little bit, n1 and n2 become different, and very easy that n1 and n2 have n1 greater than n2. Have a look on that. You displace the system by right side, but when n1 increases out of n2, these two forces, frictional forces, also get changed and f2 become greater than f. If f1 is greater, have a look on that. What will you get? If f1 is greater, you will get restoring force on the opposite side. So let's check the restoring force to check whether this motion is oscillatory SHM. 1. So the restoring force so developed is in opposite direction. You have moved the system to the right side, but the restoring force so developed can easily be calculated because both of the forces are in opposite direction. F1 is greater. So let's find out the net restoring forces. Let's subtract these restoring forces mu times n1 and mu times n2. If you can calculate easily mu mg upon 2l is there, l plus 2y minus l plus 2y, you know that you will get mu times mg upon 2l and 4y and like this. So what is the net restoring force we are getting? So the net restoring force we are getting is like this. So you are very much familiar. So what is so special about this? You are having restoring force, you are having the displacement. This force is in opposite direction to y. And what is so special about this? This is a constant that represents, of course, the spring factor of SHM. So this is representing the spring factor of SHM. And if you want to know about the time period of this SHM, so have a look on that. So this is T is equal to 2 pi under the root inertia factor, and of course the spring factor, the very easy spring factor. So M get cancelled out, and a very important answer is in front of you, that how to deal with the time period of this oscillatory SHM motion. Thank you.